Okay, last screencast. We're just going to do a quick example on Kirchoff's rules, and we're going to apply it to a circuit that's got a set of parallel resistors and two batteries. Because in this situation, you're going to have multiple equations with multiple unknowns, because you're going to need to apply both the loop rule and the junction rule to solve the problem. So we're going to do an active example. This is out of your textbook in chapter 21. Active example 21.2. It's two loops, two batteries, and we want to find the currents in the loop. So here's the circuit has a 15-volt battery over here. It's got a 9-volt battery over here. Clearly in this loop, you're going to have the current going in this direction as shown by that I1. In this loop, they show the current I2 going against that battery, and you really don't know for sure which way it's going. So if you end up getting a negative answer for I2, you know you picked the wrong direction. But you're going to assume a certain direction. So the way this problem was solved, it assumes that this 15-volt battery has a greater push than the 9-volt battery, so it's going to push the current from point A, from that junction, to the right, not to the left, but again, you don't know. So you can apply Kirchoff's loop rule to any closed loop in a circuit. There's actually three closed loops here. The first one is loop 1, shown right here around the left-hand loop. The second is loop 2, shown here on the right-hand loop. Then you would have a third one, potentially, which would be all the way around the big loop. Okay? Well, around the big loop doesn't help us solve any problems, doesn't give us any new equations with unknowns, so it's not as useful as excuse me, as applying it to the smaller loops. So let me get rid of that for now. Okay, so we're going to apply the junction rule to point A. So at point A, at point A right here, you've got I1 coming in and I2 and 3 both going out. So you've got I1 equals I2 plus I3. They write this a little differently. You can see they write it I1 minus I2 minus I3 equals 0. It's the same idea. And now they apply the loop rule to loop 1, and you assume that the current goes to the right, so that's a clockwise loop that we're doing there. So you have a positive 15 volts, and since I3 here is assumed to be going down, that means the resistor, when you go in the direction of the current, you lose voltage, you lose energy when you go across a resistor in the direction of the current. So that would be a negative I3 times that resistance, which is 100 ohms. And then you would have a negative I1 times that resistance, which is 100 ohms. So that's where you get this equation right here. So we've got three unknowns in the first equation, you've got two unknowns in the second equation. You apply the loop rule to loop 2, and you'll have a third equation that will allow you to solve for your three unknowns. So applying the loop rule, let me just erase some of the stuff over here. If you apply the loop rule to loop 2, going in the direction of the current this way, you've got a positive 9 volts. Oh, you're going against that battery, sorry. That's a negative 9 volts because you're going from the positive terminal to the negative terminal. Negative 9 volts. Now you go in the direction of the current across that resistor, so that's negative I2 times that resistor, and you're going against the current here across that last resistor, so instead of a voltage drop, you're going to have a voltage gain. So you have a plus I3 times that resistor. And again, that might be a little bit confusing because you're not going in the direction of the assumed current. You're going against the direction of the assumed current. So notice that we assumed the current was going down. When we do the loop rule this way, we're going against the current, so that would be a voltage increase across that resistor. If we're wrong on our assumed direction of the current, as I mentioned before, we'll just get a negative answer for one of the currents. So you don't have to be right in your prediction about which way the current's going, but you do have to be consistent about applying the loop rule in the constant direction. So we chose clockwise. We continued to move around in a clockwise direction, and that forced us to go in the opposite direction of the current on the left-hand side of that loop there. So as long as you're consistent, you'll get the correct answers. So now we've got a third equation right here. We've got 3 equations and 3 unknowns. So you can only solve this type of a problem with Kirchoff's rules. So it's simultaneous equations. You solve for I2 or I1 or I3, and then substitute in for that variable into another equation. I'm not going to go through the math steps to solve 3 equations simultaneously. Suffice it to say, when you do the math and you solve for one of the unknowns, substitute into another equation, solve for the third unknown, substitute into the last equation, you start to be able to solve for the unknown variables one at a time, and you get I1 is 0.070 amps. I2 is a negative 0.01 amps, so I2 actually is not going in the assumed direction, which we assumed it was going to the right. It's actually going to the left at 0.01 amps. And I3 is 0.080. That means I3 is in fact in the right direction. It does go down, and that is 0.080 amps. I1 was 0.070 amps. Okay. Again, I didn't go through the math to solve that simultaneously. I'm assuming you guys can solve the simultaneous equations. But that gives you an example of a problem that could only be solved with Kirchoff's loop rules. Okay.